Okay, let's look at some other examples of graphs to be able to look at them and apply this theorem to see whether they have Euler circuits or Euler paths. So looking at G1, notice that vertices B and D both have a degree of 3, where C and A have degree 2. So since this graph has two vertices of odd degree, we know that it has an Euler path, but no Euler circuit. And notice that, what else have we discovered from this theorem? We have discovered that in order to construct an Euler path, we must start with one of the vertices of odd degree. So in this case, we could start with D, go to A, go to B, go to C, go to D, and then back to B, and that would be an Euler path. Let's look at this larger graph here. So notice that A has degree 2, G has degree 4, F has degree 4, E has degree 2. So far we could have an Euler circuit, but now D has degree 3. So we know it doesn't have an Euler circuit at this point. It could still have an Euler path. C has degree 4, and B has degree 3. So since both B and D are the only vertices with odd degree, we know that G2 has an Euler path. Now where should we start in order to construct our Euler path? Well, we could either start at B or at D. So if we start at B, we can go all the way around the outside, and then we need to cycle back and forth, right? So we can go from C to G to B to C to F. We know that we need to end up back at the other vertex of odd degree. So that will help you to construct Euler paths. So knowing that we need to start at a vertex of odd degree and end at the other vertex of odd degree. Finally, let's look at G3. So notice that all of the vertices on the outside have degree 3. So as soon as there's more than 2, we know that G3 has neither an Euler circuit nor an Euler path. Okay, so we have developed some great characteristics to determine whether a graph has an Euler circuit or an Euler path, and it's very simple to be able to explain one way or the other whether it has or does not have an Euler circuit or an Euler path. And as you can imagine, beyond the Konigsberg problem, there are numerous applications of Euler paths and Euler circuits relating to transportation, streets in a neighborhood, roads in a transportation network, connections in a utility grid, or links in a communication network. So for each of these, we want to be able to determine whether we can meet each of our neighbors along a walk, or travel all the roads within a particular transportation network exactly one time for bus routes or whatever else you might think of. We can also look at other applications in terms of laying out circuits so that each computer is connected and all connected to each other by traveling at least each network cable exactly once, and also applications to molecular biology. So there are a number of applications of Euler paths and Euler circuits, and we have developed easy ways to be able to determine if certain graph models have them. So next we're going to look at Hamiltonian paths and circuits.